Well, good morning. It is February 11th, 2021, and what we looked at yesterday was the fact that we have different types of acceleration. We could have tangential acceleration, or we could have centripetal acceleration, which is due to the object changing direction. And as long as I know the radius and the tangential speed, the tangential velocity, I can determine the centripetal acceleration by the equation dt squared over r. And when I look at this, so yesterday we looked at the fact that, hey, friction could be what is causing that force necessary to cause that acceleration, because by Newton's second law of motion, F equals ma. In this case, my net force needs a mass, or it needs to accelerate a mass, so what is going to be providing that net force? And in the cases yesterday, it was friction. We're going to look at some other options today for the forces necessary. So if you ever wanted to join the circus and join a trapeze act, this swing is changing both its tangential velocity, because it's speeding up until it hits the bottom of the swing where it's going to have its maximum kinetic energy, but it's also changing direction. So if I have a situation where I've got an object that is swinging here, and now it is at the bottom of its swing, it is going to be accelerating towards the center when it is at the bottom. And what is going to be providing that direction there is going to be the tension of the string here is going to be what provides that tension. So if I'm down here hanging on to this string here, what has to happen is, let's say I wasn't swinging, okay? If that's the case, this weight and this tension of this swing would be equal. There's no net force. If I'm just sitting there, hanging there, these two are going to equal each other. They're going to offset each other. There's going to be no net force. There's going to be no acceleration. That's Newton's laws of motion. But if I am swinging, that means that there is a net force in this direction, okay? And what has to be providing that is there has to be an increase in the tension of this cord to provide that net force. So my net force in this case is going to equal the tension minus the weight of the person. So we're going to look at a couple examples of this and also see how the normal force can provide this same value, and also that gravity can provide that same value. So let's say I've got this situation. One of the first major movies I saw in a theater was Indiana Jones. It was Raiders of the Lost Ark. And in the opening scene of that, he swings into a pond to escape an angry group of people. And so let's say you've got an adventurous archaeologist, mass of 85 kilograms, trying to cross a river by swinging from a vine. The vine is 10 meters long, and the speed at the bottom of the swing is 8 meters per second, that should say. The breaking strength of the vine, however, is 1,000 newtons. Does he make it across the river? Okay, so let's depict this situation. Think of it in terms of free body diagrams. And you've got an 85 kilogram person. The velocity at the bottom is 8 meters per second. The radius here, which is important, is 10 meters. And the maximum tension that this vine can hold is 1,000 newtons. So let's take what we talked about previously. What is the actual tension? If the actual tension is greater than this maximum tension that this vine can hold, the cord is going to snap. If it doesn't, he's going to successfully make it across. So we've got to remember that tension is going to be what is going to be providing that net force, which allows that centripetal acceleration. So in this case, my tension, I just kind of reverse this a little bit. Instead of my tension is going to equal my weight plus my centripetal force necessary. Okay, I'm just kind of putting a little twist on it. The other way I wrote it on the other side was my net force equals my tension minus my weight. I'm just kind of reversing it a little bit, because what's going to happen here when we look at it, now we can say that my weight plus my centripetal force is going to equal my tension, because really my weight is being offset by the normal force to begin with, and then this is providing a little bit of extra kick to it. So now it's just plugging and chugging the numbers, the weight of the person, and then the centripetal force is mvt squared over r, which is the equation we gave you yesterday. So we have 833 newtons plus 544 newtons. This is going to cause a tension of 1377 newtons, which exceeds this maximum tension here. So that's 1,000 newtons. Guess what? The vine breaks and the person falls into the river. Okay? So that is one situation. That's a vine situation. Now, a lot of you guys have been crabbing about going to Valley Fair. So let's say we go to Valley Fair and we ride the roller coaster. Okay? So this roller coaster, this car has a mass of 500 kilograms, and it comes down this, and at the bottom of this arc here, there's a circle, or a semicircle, or at least the curvature of the circle would be 10 meters in radius. And then it's going to come back up a next hill, and this next hill, let's say, has a radius of 15 meters. Now, the velocity at the bottom of this first hill is 20 meters per second. What I want to know is a couple things. What is the normal force exerted on the person at this point? And then what is the speed necessary to hold this car on the track? What is the maximum speed before this car goes flying off here? Okay. Now, obviously, there's tops on the wheels, so it's not going to, but just in order to keep it on the track, so the wheels are always on the track. So let's kind of look at that, how that's going to happen. So at the bottom of the first curve, you have the weight of the car, and you would have the normal force that's going to offset that. But you also have a centripetal force right here. So the normal force is going to be this plus whatever that centripetal force is. That's going to be my normal force. My normal force is how hard this person is being pressed against the seat. And they are going to be pressed harder because that centripetal force is going to be what is providing that centripetal acceleration. It has to change directions around that curve. So here's just the plain old normal force if I only had weight, but because there's centripetal acceleration, I have more normal force here. That's going to, this is my FC, and this plus that is going to equal my normal force. So my normal force is weight plus this mvt squared over r. Notice that this is just the same thing as that tension problem, except we're approaching it from the other direction. Instead of pulling on a string, we are pushing from the bottom up. Okay? And so again, we just crunch the numbers. I've got a 500 kilogram cart. Okay? And I'm going to find out that when I crunch these numbers, that the weight itself provides 4,900 newtons of force, but notice the centripetal acceleration, the force necessary to provide that is 20,000 newtons. Notice that it's 4 times as much as just the weight itself. Okay, so when you talk about experiencing G forces at the bottom of that first hill, you'd experience greater than 4 G's of force on your body. And the human body can really only withstand certain levels. I think once a lot of people start feeling uncomfortable above 4 G's, and people who design roller coaster rides and whatnot have to take this into account. I think you start passing out at 9 G's, and I think you're going to die once you start getting above 12 or so. I'm kind of making those numbers up, but I think that's kind of the general idea. So now we need to keep the car on the track. This second hill has a little bit bigger radius of 15 meters, but I want to know the maximum velocity I can take here. Now, if this is the case, what has to happen is that I don't want this cart accelerating up, and I don't want it accelerating down. I want there to be no net force in the vertical direction. And that means that if my net force is 0, okay, that my weight has to equal the centripetal force, because those are going to, that weight is going to equal my centripetal force, because of what I want is for there to be no normal force on this cart. That's kind of what I want to be happening here. So my net force, there is a net force here, but that net force is going to be provided by the weight of the cart. There is a net force, it's due to gravity, but I want that to be provided by the weight of the cart. So my weight is going to equal the centripetal force. And so again, as always, the mass kind of falls out of the equation. The maximum velocity I can have is the square root of gr. So in this case, plug in g, plug in r, and you're going to find out that the maximum speed here is 12.1 meters per second. Now, theoretically, let's say we wanted to go around in a loop like this, kind of the same idea applies, except you need to have a speed high enough to offset this weight. You want a speed high enough where the normal force is going to make sure that you at least have a normal force. So there's going to be a threshold the other direction if you have a loop-to-loop where this weight has to be offset by the normal force pressing against this track in order for you to execute that upside down maneuver. And so we'll see problems like that, and one cohort might actually get a lab where we explore this idea a little bit. We're a little bit messed up next week because we're not going to school on Monday. So the problems that you guys are going to have are going to be right here, and you can see that, and hopefully you have no issues with that. Again, Slater, I don't know if I'm spelling that right. Slater is your friend. Look up, see what some of those answers are. Email me if you've got some questions. I'm more than happy to help. Okay, we'll talk to you guys on Friday. You guys are going to do a virtual lab tomorrow. Okay, we'll see you then. Stay warm.